In this presentation, I will explain how to use the CXL-based processing near memory called CXL PNM solution to use more effectively. After that, Choi will introduce our memory box solution that can be linked with the CXL PNM. This is introduction to processing in memory and processing near memory called PIM and PNM are novel technologies that integrate computation logic and memory semiconductors. By performing computation near memory, it is effective for memory-intensive operation. However, the end-to-end AI and machine learning inference involves both computation-intensive and memory-intensive operations. So in this session, this presentation addressed a method for effectively using the CXL PNM in the heterogeneous system, including CPU, GPU, and our CXL PNM device. First, I would like to talk about the PIM and PNM solutions. Both PIM and PNM solutions can reduce data movement between the host processor and memory by computation near memory. In our case, HBM PIM, AXDIM, Smart SSD, and our CXL PNM solution have been developed and put data transparency and processing closer to memory. However, these solutions are only effective for memory-intensive operations. The ML-based application involves both memory-intensive and compute-intensive operations. So this presentation introduces an example of ML applications, deep learning-based recommendation model called DLRM, which predict user interacts based on their experience. In the DLRM inference, dense features such as age and height is processed in compute-intensive pre-connected layer, while the sparse feature such as a type and gender is processed through the memory-intensive embedding lookup operations. So before introducing our work, I would like to introduce our PNM solution. We have developed many PNM solutions that operate on the DIM interface and CXL interface. So this figure shows that our PNM device, such as AXDIM and CMM DC, CXL memory module with the DRAM compute called CMM DC, and it is placed on accelerator logic between CXL IP and memory controllers. This figure shows the typical architecture of the CXL PNM controller. It is designed to not only operate as a CXL Type 3 memory expansion, but also effectively manages its accelerator logic. The CXL data path is used to use a sideband interface for the host processor to configure, program, and control the accelerator logic. In the CXL PNM for DLRM acceleration, the host processor can configure, program the PNM engine using the CXL data path and read the result through the CXL daemon path. So now I would like to talk about the performing the end-to-end DLRM inference using XPU and our CMM DC device. When used with the host processor that can support CXL protocol, the host processor and CXL PNM can improve the performance by performing the computations that they are good at in parallel. So in this case, CXL support processor can conduct a compute-intensive operations such as a pre-connected layer, and our CMM DC device can conduct a memory-intensive embedding lookup operation. The embedding lookup operation on our CXL PNM device is performing sequentially through the instruction write, performing computation, reading result, and register pulling to check the completion. During the computation process in the CXL PNM device, the start and completion check are operated on the CXL.io path and register pairing mechanism. Due to the protocol overhead of the CXL.io path, relatively higher latency is consumed than CXL timeline path. To improve the latency, we solved the problem by allowing the host processor to view the CXL PNM's configuration register as a CXL.mem path. By changing the register pairing from the CXL.io path to CXL.mem path, the consumed time to check the start and finish of the operation at embedding lookup has been dramatically reduced. The execution time of the embedding lookup was improved from about 80% to about 7% of the total time, and it can lead to performance improvement in the end-to-end DRM inference latency and throughput. In summary, the latency was improved by about 80% compared to using the data.io path, and the throughput was improved by about 4.2 times higher. Currently, our software stack of the CXL PNM is designed to be comparable with the PyTorch version 1's API. So we are planning to implement it with UXL, considering integration with our CXL PNM solutions. So I introduce CXL PNM part, and Choi will introduce our CXL memory module box.
Okay, thank you, Sangsu. Okay. Okay, so how about have a bunch of CMM DC in a one box? For that context, we also developed a CXL memory module box. That this box could host heterogeneous CMM memories that include CMMD, CMMH, and CMMDC. CMMD is composed of DRAM only. CMMH is composed of DRAM plus NAND flash. And CMMDC, as Sangsu mentioned, that CMMDC is a CMMD plus computation. This memory appliance could be used disaggregated composable memory box. It could provide memory pooling and memory sharing features. It supports CXL 1.1 and CXL 2.0 protocol. We made this one for rack mountable chassis. So you could install this memory box in the rack without any issues. In addition to memory box itself, we also developed a fabric orchestrator called the Samsung Cognos Management Console. I will briefly explain that modules in the following slide. Okay. In addition to box itself, we collaborate with Supermicro, and we developed a rack scale composable memory bank solution. With this rack scale composable memory bank, we could get a highly scalable and composable CXL memory pooling and sharing systems. Also, we could host a processing memory device here, so you could get a bunch of CXL memory and processing memory devices also. This is a future-proof memory capacity and bandwidth scalable solutions, and we provide this one as a kind of a turnkey solution. As you may already know, when you play with CXL, there is a lot of complication, including server BIOS configuration stuff to make it correctly and work well. But with this rack scale composable memory bank solution, you don't have to put your high effort for that, because this is a kind of preset configuration. You could just allocate memory to your servers and just run it. This is also for TCO enhancement solutions. Many people already discussed the memory stranding issues in talks, these sessions. So with this dynamic memory allocation and memory pooling, we could avoid memory stranding issue, and we could allocate on-demand memory based on the capacity and bandwidth requirement. And also we could offload processing to CMM DC that Sangsu presented. As I briefly mentioned that, we also developed a fabric orchestrator. So this memory fabric orchestrator is aligned to OCP CMS DC memory fabric orchestration subteam architecture. It supports REST API. It shows some performance metrics. In addition to that, we could this could show the host memory utilization and statistics. In addition to development itself, we ran a cutting-edge in-memory database that is widely used in the industry. That is a SAP HANA. Here we set up two systems. The first system in the left, we allocate the one CMMD device, and we set up a second server with a higher capacity and more bandwidth. So capacity-wise, as you add more as you allocate more CMMD device, you could get a capacity scalability. In this case, we could get a 7x capacity scalability. And also we add 2x bandwidth. We allocate 2x bandwidth to second server. With this environment, we could get 32% end-to-end SAP HANA performance when we run TPC DS on top of SAP HANA. This is a real-time performance measurement. Lastly, I want to call to actions. This CXL stuff is mainly related to OCP CMS project. So I invite you to participate in composable memory system development and enablement. As we discussed, there are many things we need to address, including programming model development and how we could make more scale and secure. In addition to that, OCP has a data-centric computing workstream. A data-centric computing workstream is actively discuss processing in memory capability and also computation in storage. So I invite you to participate in OCP DCC also. Okay, thank you for listening to my talk.